Hello everyone. Today in this video, we are dealing with a frame structure element by using the stiffness matrix method for analyzing that structure. This video might actually help you to go through the project for this weekend. However, I can't actually give you the exact same example so that you can just copy and paste, right? So I prepared a slightly different but almost similar example so that you can learn from this one and you can implement into your the frame analysis project. So I prepared this kind of structure. So this is consists of a column and then beam, the 8-meter span beam, and equal span, an equal length of the column as a left hand side of column. So loading condition, that figure is quite mess, but you can still figure out what the load conditions are. So load conditions, I gave a 0.5 kilonewton per meter UDL, and I applied the column weight into the node 2 and 4 as a 1 kilonewton in there, and also add 5 kilonewton point loading, the concentrated load at node 3, and I numbered the nodes from the left to the right around the structure. So further left bottom, starting from the 1, 2, 3, 4, 5, and your element number will look like 1 and direction 1 to 2, 2 direction 2 to 3, your third element direction node 3 to 4, your number 4 of your element is direction 4 to 5. In terms of the numbering of degree of freedoms, it will be numbered 3 degree of freedoms first, and we are numbering the x, y moment in order, and we'll order numbering from the left to the right. Alright, let's first number the 3 degree of freedom first. As entire things is totally fixed, we skip that, and your second one, so starting from the x, y moment, so 1, 2, 3, and move on to the next one, 4, 5, 6, or everything is free, and moving on to your fourth node, and 7, 8, 9, everything is free to rotate, free to move, free to move in a y direction as well. And your fifth one, everything is fixed. So come back to your first node to number the fixed degree of freedom from the XY moment, so 10, 11, 12, and moving on to your next fixed degree of freedom, which is a fifth node. So then X, Y, Z, 13, 14, 15. So pretty much your global stiffness matrix look like 15 by 15 matrix, right? You've got the properties right over there. Area is given by 8.0 times by 10 to the power of minus 3 cubic meter, and your moment of inertia is given as 8. Alright, let's dig in to the MATLAB code. So in this video, I'm not gonna actually type in to waste your time. So I'm just gonna go through what my MATLAB code look like, and also you can just sit and open the MATLAB and then type as you watching this video. Then you might actually learn something from here. The first thing first, so we just give them. By the way, I typed everything in the live editor, which might actually be easier for you to work with. So I'm working with the meter Newton particles, and I gave the sectional properties for the area, your moment of inertia, your Young's modulus, everything is given as is. And then I moved on to type on like a matrix of nodal coordinates. Each row of my matrix is given by XY format. So I completed like my matrix called like nodes. I added like your first node 0, 0, and your second node 0, 2, your third node 4, 2, and your fourth node is going to be 8, 2, your fifth node 8, 0. So pretty much you're typing in your just coordinate over each node. And also I want to declare the matrix elements connectivity. So basically it is just claiming the element connection from like a node 1 to 2 or 2 to 3, 3 to 4, 4 to 5, and so on. So we have a vector called conn, C-O-N-N. So your first element is connection between first node and the second node. Second node to third node gives the element 2 and 3, 4, and so on. So you can customize everything. If your node numbering is different, you can also change like the order of that one. Also, that connection might actually change slightly. So we can move on. And this one, I'm generating some empty vectors and event matrices for storing some values. So I am actually creating quite a lot of them. So this NEL is like a number of elements, and like an N node is a number of nodes in the entire structure, and the number of degree of freedoms, since like in the frame structure you've got 3 degree of freedoms per node, so then you can times by 3 of the number of nodes to get the entire number of degree of freedoms. So then I created the length vector, which is allocating the each element's length, and I also created angles vector, just like storing the angles between the of each element. And I created the empty vector. So you probably actually realize that you can actually use a zeros function in MATLAB to create the empty vector. So your global stiffness matrix look like NDOF times NDOF. So like a number of degree of freedom by number of degree of freedom, which is a 15 by 15 zeros vector. And you've got like a number of degree of freedom by 1, which is a vector, and then you've got 15 different slots for filling in your force vector. So there's like a displacement vector as well. This is like arrays of array, KEL store, index store, rotation store, but these are also empty vector by using the self function. So I'm actually going through once they are appeared in the code. I will explain what these are. So first, like we want to calculate the length and the angle of each element. So I use a for loops, just going through the entire element to find out what your first node and the second node is, and then calling what is the near x and the far x and the near y and the far y, and finding out the difference in x and the difference in y, and then by using that you can calculate your length and then angles, and then putting into your first, second, third, and the fourth your entire element, and then storing into the right position, and then you can get these results. And you don't have to worry about this point. This is just like a outputting like your angles and the length in looking like that one. If you want to actually implement it, you can do that, but you don't have to do it. This is just for the visual purpose. Alright, then we actually move on to define your boundary conditions and then find out your displacement vector. So as we said, we have 9 of free degree of freedoms and then 6 of fixed degree of freedoms, right? So then logical means you are creating the logical vector or matrix, whatever you are putting in here. So I am creating, so first, second, third, 4, 5, 6, 7, 8, 9 3 degree of freedoms are my f free vector, and then the other things are all 0, and then not f, whatever it like f looks like just giving the just completely opposite of that one. So like these two will be logical vector, consists of like either 1 or 0, like the computer. And I specify your fixed degree of freedoms of your displacement vector is a 0. Right, straightforward. And yeah, load vector sampling. So this is a point you might actually get confused, but I can go through slowly. I can just give this one next to it. Alright, let's first go to the second one. So we have 1, 2, 3 degree freedoms, and your 1 kilonewton, it goes directly into your second degree of freedom. Then you'll add like a -1 kilonewton, and your distribution loading 0.5 kilonewton per meter for the 4 meter element length, and the half of them goes into 2, right? And then this is the effect of the equivalent loading from the distributed loading. And your third degree of freedom, which is a rotation degree of freedom, and you can use WL squared over 12, and this is the result, and I put there. And moving on to the third one, you've got 5 kilonewton down, and you've got a equivalent loading from the UDL from the left hand side, your second element, so does like a third element as well. So then you are counting the 2 of WL divided by 2, and your direct nodal force in the y direction, so fifth degree of freedom direction here, and then you simply add in here 5,000 Newton. Your sixth degree of freedom, the rotation degree of freedom, apparently this is a 0 because it is a continuous, and then your intensity of the UDL is the same left and right hand side. So these are exactly the same magnitude, but this one gives minus, positive, minus, and positive on the right hand side. So like minus, plus, minus added up together, and then this comes up landed at 0. And we can move on to 8, which is exactly the same as your second degree of freedom. So I just copied it, or you could actually say that as a 2. And F9, that is going to be positive sign of your third degree of freedom's loading. Alright, I'm pretty sure you understand like what's actually cooking here. And I actually saved the external loading. These are actually equivalent loading from the external loadings, right, into like each degree of freedoms. I separately saved it for calculating reaction force for later. So then we have F vector and we have F external loading vector separately. So now at this point, these are identical right now. Then apparently you can actually calculate like through the for loop, like to calculate the index function, index vector. However, to make it everything easy, I just like a manually typed in here. So basically I generate the index vectors. That curly bracket is you are calling a vector from the arrays of array. So basically you are calling from the index store, you are storing the vectors. So yeah, you are storing the vectors into the arrays. So then calling the first vector, which is your connectivity, so your degree of freedom between the node 1 to 2. So basically you're working in the first element degree of freedom indexes. So then it's going to be 10, 11, 12, and your 1, 2, 3 degree of freedoms. I can actually put it here as well. Right there. This might actually help you to understand further. Alright, and then your second index is going to be 1, 2, 3, 4, 5, 6. Third one, 4, 5, 6, 7, 8, 9. And then your fourth one is going to be 7, 8, 9, 13, 14, 15. Because of your direction, like a beam orientation, you were actually starting deciding the orientation goes like from 4 to 5. So this is your index for assembling your global matrix later from the local stiffness matrix. Right, now we can go on with a global stiffness matrix assembly. So basically getting a for loop from the going through entire element, calling the index store and the index function, index vector, and assigning it to a variable int, and assigning a variable L by using the length function. So calling each element's length, call like each element's angles, and then put it into the S and C to calculate a rotational matrix for each element's transformation matrix. You probably familiarized with this matrix by this time, and I'm saving that rotational form the rotational like a transformation matrix into rot store, storing the rotational rot store. And then to calculate out local stiffness matrix, I uses just, you can actually put like AE over L minus AE over L minus AE over L, AE over L, but I just took that one common factors out as a C1 and the C2. I calculated it here for each element, and then calculate out your bar element stiffness matrix and your beam stiffness matrix, and frame is combination of those two. So KEL bar plus KL beam. So just giving an idea. So at this stage, KEL is an element stiffness matrix in local coordinate system. But you need to actually assemble that into global coordinate system, because like you need to take account of the orientation of your beam or a column or a bar, whatever your structure element is. So how you do that is your transport of transformation matrix times KEL in local coordinate times transformation matrix gives you your element stiffness matrix in global coordinate system. So I call it KEL rotation. So KL rot. So now we need to just assign into global, populating them into global stiffness matrix. So what it does, in the global stiffness matrix, calling the index vectors the sub-matrix, just like condensed matrix, index vectors row by index vectors columns, and then adding what the values are with the rotated element local stiffness matrix. And then you basically you sum up and then you top up all the values, and then afterwards you can get stiffness matrix. Look like that. Oops, sorry. Your stiffness matrix. Okay, these are quite big, so I will actually provide global stiffness matrix later as a separate file, so that you can also compare your answers for this example. Then now we can actually solve for the solver function. We've got partitioned systems of equations for the stiffness method. So we need KFF and then KSF. Basically we need like K11 and we need K21. So I call it KFF and then KSF, freedom, and then specified freedom. So then you can find out your unknown displacement where free degree of freedoms are, so allowed to rotate or allowed to translate. So then your df is going to be kff. So this is inverse, that times by the inverse of kff. So then times by the force vector of the free degree of freedoms minus kfs times the ds. However, the ds, everything ds is a 0, so it can be simplified into df equals kff inverse times ff. So this gives you all the displacement for the free degree of freedoms, but some values are just too small, but like making it quite tedious to look at. So I'm just clearing significantly small number, going through the entire displacement factor. Whatever it's like smaller than like 10 to the power of minus 10 equals 0. But remember that must be the absolute value, because otherwise you are erasing everything negative values. So this gives df, so free degree of freedoms displacements. ds that is simple, that is a 0. So d metrics look like these things, and then the other things are 0. And now we can find the reaction forces for the fixed degree of freedoms are. So F specified like a fixed degree of freedoms equals KSF, which we actually calculated at there, and plus KSS times DS, but like this thing is going to be 0, right? But remember your force vector, your F net, is consisted of your equivalent loading plus the reaction force. So to get the reaction force, subtract from the left hand side, from the right hand side, with the external loading vector. So now I can use like the FEXT load vector. So after this stage, your F vector and then your FEXT load vector is going to be look different. So then I'll call it F reaction. Then it comes out your 10, 11, 12, 13, 14, 15 degree of freedoms reaction forces look like. If you do the balance check, you will see the reaction force and your external loadings are equivalent to each other. So just giving an idea how it looks with the Procon model. So you've got 1.7 millimeter down displacement at node 3. So this is 1, 2, 3, 4, 5. So your 50-degree freedom is displaced as a 1.72 millimeter. And for the reaction force, 5.50. Okay, these are all good. And your x-directional reaction force is a 502, and then we got 5017, so close enough. And the reaction moments is also they are also same. Alright guys, try to learn this example also, and then you can implement the practical example into the frame analysis project. Alright, I hope this video helped you, and then our workshop load K matrix and KFF and KSF matrix so that you can compare the answer. Great, thanks.